All right, last section of the last unit. Here we go. Chemistry 3202 review, Electrochemical Cells. Okay, in this particular lesson, what we're going to do is we're going to look at how we would set up an electrochemical cell to create an electric voltage that we could use. Because we know in the last section that we were talking about redox reactions of how one substance would be oxidized and produced electrons, and another substance would be reduced and would gain those electrons. In the process, what we want to be able to do is we want to harness those electrons. We want to be able to capture them so that they can do work for us. So we want to have them in, say, an iPod. We want to have it in a battery in a cell phone, or we want to be able to run an electric motor or a light bulb in a flashlight. So we want to be able to harness these electrons as they go from being the oxidation reaction to the reduction reaction. So here we go. Here are the outcomes for this lesson. Okay, and electrochemistry, we're saying, is the study of converting chemical energy into electrical energy, and it's based on the redox reaction, the oxidation reduction. And I said what we're going to be doing here now is being able to capture these electrons to do work for us, or we're going to look at another situation in another lesson where we can actually recharge a battery. So when your iPod goes dead, how do we go about recharging it? And it will be the reverse of an electrochemical reaction, where the battery would discharge so that we could use the energy. So we're going to look at both situations here. So let's have a look. The very first cell we're going to look at is what's called a galvanic cell, or it can also be called an electrochemical cell. All right, so another name for a galvanic cell is electrochemical cell. So I'm going to put that there, because many times we use the names interchangeably, and sometimes people think it's two different things, but it's really an electrochemical cell. And we would refer to it as a galvanic cell. There we go. So same thing, one and the same. When we refer to a galvanic cell, we're referring to an electrochemical cell. Sometimes a galvanic cell is also known as a voltaic cell. All right, so three names for the same sort of thing that's happening here. And what we have here is we have it's set up. Now this is a crude electrochemical cell, but it's going to work nonetheless. This is nothing like what's in a, say, a 9-volt battery or a car battery. It's very similar, but what we have here is two glass beakers, which makes it a little bit impractical, but it's going to be able to show you what's going on with the cell itself to get the electricity. So it's made up of two half cells. Now we've seen that notation before. When we balanced electrochemical reactions, redox reactions, we would break it down to its oxidation half reaction and its reduction half reaction. So what we have here is in each of these cells we're going to have oxidation occurring in one cell and reduction occurring in another, and hence the idea that we have two half cells. So we've separated the two halves of the redox reaction. And we also have to make sure that we're going to be separated by something called a salt bridge, which is this little device here. And all this salt bridge is just simply a plastic tube or a glass tube that's filled up with an electrolyte, and we're going to make reference to that now in a few minutes. But at the ends of the electrolyte, it's capped off with some kind of porous barrier, like plaster of Paris, you know, like you have gyprock in your house, that sort of material, the plaster of Paris. And then what that does is when it hardens, it creates a porous barrier so that the liquid cannot flow. But because it's a porous barrier, ions can move through it. All right, so that's what's happening in this salt bridge. So it's an electrolyte solution that's been capped off, so the electrolyte cannot flow out freely, but it's restricted by that porous barrier there. And another way we could do this is we can look at something called a porous barrier. Now I'm going to look at that one in a little more detail in a second here now. Each half cell contains something called an electrode and an electrolyte. Okay, so I've got a little bit cut off there, so that's simply saying an electrode and an electrolyte. And we're looking at this and we're saying, okay, that piece of zinc metal, that's acting as an electrode, and that piece of copper metal is going to be another electrode. What these guys are immersed in is what's called an electrolyte, which is basically an ionic compound that's been dissolved. All right, so there's free-moving ions in that particular solution. And generally speaking, the way we set up these cells is that if we're going to use zinc as an electrode, we're going to immerse it in a solution of zinc ions. And if we're going to use copper, we're going to immerse it in a solution of copper ions. Now this sulfate that comes along with it, that's going to be spectator for the most part, but it will have a little bit of a function here. But for the most part, the sulfate's job was basically to get the zinc into solution and the copper into solution. So whatever we use here, it's going to have to be a highly soluble form of the metal ion. So zinc sulfate, zinc nitrate, things of that nature. All right, here we go. The electrons are going to spontaneously flow from the oxidation half reaction to the redox or the reduction half reaction. So why would that make sense? Well, oxidation is a situation where the electrons are being produced. So in an oxidation reaction, electrons are being produced as a product, so the electrons are going to move away from the reaction where there's oxidation. And in reduction, the electrons are being consumed, so electrons are going to move towards the reduction equation. All right, and the electrons are going to move through the wire. And because the electrons move through the wire, we can actually harness these electrons, and we can have something here that's going to require a voltage like an iPod or a telephone, cell phone, or a motor, an electric motor, or a light bulb, or something of that nature, something that's going to consume the energy as the electrons flow through it. The flow of ions, as we start getting a buildup of ions, that's what the purpose of the salt bridge is. It's like an ion gatekeeper so that it can control the level of ions in each of these containers so that the electrical neutrality is never out of whack. All right, we don't want the electrical neutrality to start to go out of sync here. That is, we don't want one of these cells to become more positive or more negative than the other. And we'll look at that now in a second. Okay. One of the things we have to say here, as I've already mentioned, the electrolytes that zinc is dissolved in has to be highly soluble. So we can't put something here with zinc that's not going to dissolve in water, because if it doesn't dissolve in water, then it's not going to free up the zinc ions in order for a chemical reaction to occur. Likewise with copper, it has to be something that's going to be very highly soluble so that we can free up the copper ions. Okay? And the cell will not work if the salts of the electrode are insoluble. So if we put something there like that doesn't dissolve, then we're not going to get the free ions. Okay, so we need free metal ions to get this stuff moving. And that's a very important point here. And we can put a little Sasquatchy footnote by that. There we go. Little Sasquatchy footnote. Very important that it has to be soluble. Okay, let's go and look at what's going on with this very same electrochemical cell. So we're looking at this and we're saying, all right, in one of these containers we're going to see oxidation. The oxidation is going to occur in the zinc electrode. So what's going to happen in the zinc electrode is we're going to produce some oxidation of zinc metal. So in this particular electrode we're going to see the oxidation, and what's going to happen here is the zinc metal from the electrode is going to be broken down to produce zinc ions and 2 electrons. Now what happens is, as this switch is closed up above, the electrons are going to start flowing in this direction. All right, so the electrons start flowing in this direction through the circuit. All right, and in this case, because we're getting a buildup of electrons on the zinc, this particular piece of wire in the zinc electrode is going to be negatively charged. Hence, we would refer to it as a negative charge, the anode. So whenever if you had to pop the hood on your car and looked at your car battery, the negative terminal is what's referred to as the anode, just generally the one with the black wire. All right, so the anode is the negative terminal. And this is why it's negative, because it's producing electrons. So as the zinc is being converted to zinc ions, electrons are being produced, and the electrons that are produced are flowing through the wire. The zinc ions make their way to the solution. Okay, now remember, Leo is an ox. Loss of electrons is oxidation. Well, we want to take this a step forward, because if loss of electrons is oxidation, that occurs on the anode. So that's what the AN is. Leo in anox is anode. And the anode is going to be negative. So what we have to keep in mind is that by definition, the site of oxidation is always going to be the anode. So how do you determine which one is going to be the anode? Well, you have to figure out which one the oxidation reaction is occurring in. So the anode is the site of oxidation. So what's going on here then as the electrons flow? Well, the electrons are going to make their way over to the other terminal, but before we go to that route, as the electrons are flowing over, we're also getting the production of zinc ions. So the concentration of zinc ions is starting to increase here. So we're going to get a buildup of positive charge in this particular solution, because as more and more reaction, as more and more zinc gets oxidized, more and more zinc ions are being produced. So the concentration of this is beginning to rise. Now we don't want that to rise. We want this container to maintain its electrical neutrality. So what we have up here in our salt bridge is a very soluble solution of potassium nitrate. So what happens here to the potassium nitrate is, because we get a buildup of positive charge here, it's going to start pulling the negative nitrate ions in that direction. So as this reaction proceeds, the anions, the nitrate ions in this case, NO3, are going to start being pulled in this direction. And in doing so, as the nitrate ions are pulled through this porous barrier, what's going to happen is the negative charges are going to neutralize the excess positive that's being produced here. So as the concentration of zinc 2+ goes up, the nitrate is being pulled out to try and counterbalance the electrical neutrality here. And a way we can remember that is anions, which are the negative nitrate ions, are always going to move to the anode, right? Leo is anox, anions to the anode. All right, so there we go. So we've taken care of the electrical neutrality here. We have electrons flowing in this direction, going through your iPod, playing all that fantastic music. And all of a sudden, that's high energy electrons that are going in there, high energy electrons going in. What's coming out of your iPod is going to be low energy electrons, but electrons nonetheless. So as these electrons come down through here, as soon as they hit the copper electrode, the copper ions are going to start picking them up. So what we see happening on this electrode, on the surface of the copper, is reduction. So as those electrons are being passed through the iPod and being used up, they're coming out in low energy, they're being picked up by the copper, and what's happening is we're getting the production of copper solid. So in the zinc electrode, or the zinc half cell, we're seeing oxidation. In the copper half cell, we're seeing reduction. And we're looking at this and we're saying, okay, in this case, the copper 2+ now, in terms of the electric charge here, as the copper is being consumed, what's happening, its concentration is dropping. So this cell over here is becoming less positive. Less positive means more negative, which means I need to replace these positive charge as they're being removed. So what happens here is the cations in the salt bridge start to get pulled in that direction. So in this particular case, the K+ starts to pull in this direction to replace the lost copper. So in this case, the K+ would go out into that solution and try to keep the electrical neutrality the same to try and replace the lost copper. So there we go. And another point to note here is the cathode is the site of reduction. But we don't have to keep that in mind, because we know from the other side that the anode is the site of oxidation. So in this particular example, because the reduction is occurring in this half cell, this is a cathode, and this guy's going to have positive charge. As soon as these electrons come down here, they disappear. On this side, we're seeing a buildup of electrons, because as this reaction keeps going further and further and further forward, more and more electrons are being produced. So these guys are being pushed on, which makes this piece of wire negative. Okay. Now, a couple things we have to keep in mind here is, if copper ions are producing copper solid, then what we're going to start seeing in this particular reaction on this electrode is we're going to start seeing a buildup of copper. So the copper electrode is going to start to get bigger because copper is building up on that electrode from this reaction. Copper solid is being produced. In this reaction, the zinc is being consumed. So what we're going to see on the zinc side is the zinc electrode is going to start to disappear. And as we start getting the reaction to go further and further and further, more and more and more of the zinc begins to disappear. Okay, that's because it's being consumed. So how long could this battery last? Well, this battery could keep producing an electric current until all of the zinc electrode was completely consumed, all used up. Or maybe the salt bridge nitrate ions or potassium ions get completely consumed, because if there's no more nitrate ions, then what happens, we can no longer keep this electrically neutral. So the battery's going to start to die, get weaker and weaker and weaker. So if the salt bridge runs out, that's rare. Or at the same time, if the copper ions get all used up, then obviously the reduction can't happen. And remember, you can't have oxidation if you don't have reduction. So this is happening simultaneously at the same time in both of these half cells, because you can't have one without the other. Okay? And there we go. So over time, of course, as the copper begins to get depleted, the battery starts to lose its push, and therefore it begins to go dead. All right. The salt bridge is very important. Okay. The salt bridge, its main purpose, its only purpose, is to control the flow of ions so that each of the half cells remains electrically neutral. As soon as the positive or negative charge begins to build up, that's going to cause, remember Le Chatelier's principle in equilibrium? If one of these electrons or these ions begins to build up, it's going to cause the reaction to reverse itself or slow down. It's not going to reverse, it's simply going to slow down. Everything builds up, so it's going to be harder to go forward, therefore the reaction begins to go dead. So without the electrical neutrality being maintained, the battery will go dead really, really quickly. All right, so that's the purpose of the salt bridge. What's in the salt bridge is very important, because it too has to be very highly soluble, and it has to be something that doesn't interfere with what's going on in the half cells. And let's see what that's all about. All right, so in this particular system, we have to have something that's highly soluble, so that's why we like to choose nitrates, because you know from your 2202 and your Science 1206 that from the solubility table, all nitrates are aqueous. And when we talk about getting something that's not going to compete with the ions in the cell, here's an example. Suppose I had silver as one of my half reactions. If I use potassium chloride in my salt bridge, it would be okay, because potassium chloride is very highly soluble, because potassium is a group 1 metal. Very highly soluble, so we're going to get it breaking down into ions. The only problem is, if the chloride ions should happen to move to the half cell where silver ions are, then the silver ions are going to be precipitated as a solid, and the silver will no longer be available to be reduced. All right? So what we got to keep in mind, here's the solubility table that they give you on the public exam. You know, it's there for a reason, because you may have to use it at times. We can use this, and just as a refresher, look, all nitrates are going to be very highly soluble, so all nitrates are aqueous. So that's a good choice for our salt bridge, because no matter what metal ions are in those two containers, the nitrates are not going to interfere, because none of them are going to be precipitated out. Here's the situation with chlorine. If I use potassium chloride, it's going to be very highly soluble, but not with silver. So that would be a competing reaction for the silver ion. It would no longer be available to be reduced, so I'd have to watch that. Other ones that compete with silver, like lead, mercury, copper. Some other important ones, we got to watch out for sulfates, because look at all the ones that are exceptions for sulfate. You know, if you had a barium or a strontium ion there, it's going to precipitate as a solid. It's going to be a competing reaction. Therefore, it may not be suitable as a salt bridge electrolyte. So that's what you have to watch out for. So on multiple choice, they'll say, you know, which is a suitable electrolyte for the salt bridge. Potassium nitrate is always perfect, but suppose that one's not given to you. Suppose they ask you, what about a sulfide? Well, look, almost every single sulfide with metals, like iron, nickel, copper, every single one of those is going to be competing with sulfide. It's going to precipitate out. So we got to watch that. Hydroxides are not a good choice because most hydroxides are going to be insoluble. Most carbonates, phosphates, sulfites, right? Not very suitable as salt bridges depending on what metal they're being matched with. So again, the best bet is a nitrate compound, but you got to watch it. Okay? So use your solubility table to help figure that out. Now, remember we talked about balancing equations in redox, where you was either acidic or basic. You got to watch that too here, because if you use hydroxide as your electrolyte in your salt bridge, suppose the hydroxide gets pulled to one cell. Now all of a sudden that could fool up. If that cell is being carried out in acidic conditions, then this hydroxide is going to neutralize your acidity, and therefore that redox half reaction will not happen because it's not going to be no longer acidic conditions. Same thing is true with ammonia. If you use ammonia as a salt bridge material, then that's going to have acidic properties, and it's going to fool up the chemistry there. So you got to be very careful about what's in the salt bridge. So the best bet is potassium nitrate. That's going to work with just about everything. All right, so watch out. As we said, anions flow to the anode in the salt bridge, cations flow to the cathode in the salt bridge. And here's the business with the porous barrier that we talked about. This is what's called a Daniell cell, and the porous barrier takes the place of the salt bridge. So that as we get a buildup of zinc ions, the same sort of chemical reactions happening, right? Zinc is being oxidized to produce zinc, copper ions being reduced. So what happens is, as this potential occurs, the zinc ions are going to be pulled through this porous barrier. All right, so we don't need the salt bridge, providing that the porous barrier doesn't leak anywhere. If it leaks, then the cell's not going to work, because we have to be able to set up this gradient here. So what happens is the ions are pulled through to try and balance out the charge. All right, so again, anions are going to flow to the anode. Cations are going to be pulled to the cathode. Same principle, just a slightly different setup. Okay. Now, we don't want to be writing out these cells. We don't want to be able to drawing pictures like this all the time. All right. We want to be able to do this in shorthand notation, because this is quite complicated, what's going on here. Be able to do that too, by the way. Sometimes on the exam they ask you to draw a diagram of an electrochemical cell, state which one is the anode, which is the cathode, show the movement of electrons from the anode to the cathode, show what's happening in the salt bridge, right? Anions to the anode, cations to the cathode. So sometimes they expect you to do a little sketch here. Okay? But what we want to be able to do is represent this in shorthand notation, and this is the accepted way that we do this. And shorthand notation looks something like this. All right, let me just reveal the whole thing here. With shorthand notation, what they're saying is we want to be able to represent what's going on in this cell without showing all the nitty-gritty there. So what we're saying is the anode, what's happening with the zinc, is always going to be on the left-hand side, and the cathode is always going to be positioned on the right-hand side. No matter what type of cell we're doing, the anode is always on the left. The double pipe here, this little symbol here is called a pipe symbol. The double pipe is what represents the salt bridge or porous barrier. This is what separates the anode from the cathode. All right? The single pipe represents a phase change or a boundary change. So in this case, zinc solid is in a different phase than zinc aqueous. So we would represent that with a single line showing you that a phase change is occurring, or we're in a different boundary. We're in solid on this side, this is aqueous. So situations where we would get a boundary change could be between a solid and aqueous, or solid to a gas, or solid to a liquid, or vice versa. All right. So in this case, zinc solid going to aqueous, boundary change. Salt bridge, copper ions being reduced to copper metal, boundary change. Okay, boundary change. So we've got aqueous going to solid. Okay, and that would be the shorthand notation. So this is showing me the oxidation half reaction. zinc going to zinc ions and 2 electrons, and the reduction will be showing me copper 2 plus going to copper solid gaining 2 electrons. If we wanted to write the overall equation, we have to watch out here because after all, the actual reaction, if I can write the half reactions, is going to look something like this. It's going to be zinc solid going to zinc ions and 2 electrons, whereas with the copper, it's going to be copper ions gaining 2 electrons to produce copper metal. So when we rewrite this, of course, what we're seeing is zinc going to zinc ions, zinc going to zinc ions, zinc going to zinc ions, copper ions going to copper, copper ions going to copper, copper ions going to copper. Get it? All right, so that's shorthand notation. Let's do a couple of examples. Okay, here's an example where we're looking at the reaction between iron and nickel nitrate, producing iron nitrate and nickel. So we want to sketch an electrochemical cell of this. So we say, okay, no sweat, we can do this. Okay, we can do this. I'm simply going to draw my 2 beakers. Only a sketch, by the way, doesn't have to be perfect. There's my 2 beakers, and I'm going to draw it the way it's written. Okay, in this particular, okay, let me just draw this again. Okay, I'm going to have a piece of iron and a piece of nickel as my electrodes. So that's going to be Fe, and that's going to be nickel. That's going to be immersed in a solution of its own ion. So it's going to be in a solution of Fe2+, and in this case nitrate is coming along as spectator. And the other half cell is going to be immersed in its own ion, nickel 2+, and so a nitrate is coming along as a spectator. Don't forget our salt bridge, because we have to somehow keep this connected. We need a complete loop here. So there's our salt bridge. And in that salt bridge, I'm going to play it safe. I'm going to put potassium nitrate here. All right. I'm going to hook up my 2 electrodes, and I'm going to have my device, which is going to measure a voltage. There we go. The half reaction is showing me up here, I'm seeing Fe solid being reacted with nickel ions to produce Fe ions and nickel solid. So I know which one's being oxidized. It's the iron that's being oxidized. So in this half cell, we've got Fe solid producing Fe2+ and 2 electrons. So this is oxidation, which makes this the site of, or sorry, makes this the anode, because remember, Leo is anox, and the anode is going to be the site of oxidation, which makes the iron negative, because it's the anode. Electrons are being produced here. Okay? As the electrons are being produced, the iron concentration is going up, up, and up, and up. So what's going to have to happen here is the anions are going to flow to the anode. So in this case, the nitrate ions are going to be pulled in that direction, anions to the anode. At the same time, as these electrons are coming back to the nickel 2+ is going to go and gobble them up right away. So we're going to see nickel 2+ accepting these electrons to produce nickel metal. And this is going to be the reduction half reaction, which makes this the cathode, because the cathode is the site of reduction. So this guy is going to be positive, and it's going to be the cathode. See the T in cathode? Like a plus sign, isn't it? Cathode. There we go. As the nickel ions are removed, the cell's becoming less and less positive, so we need to replace the positive by saying cations move to the cathode. There we go. All right, so that's the cell. Okay, it says assume the salt bridge is used to connect the cells. Suggest an electrolyte. Well, we already did. Something that's highly soluble, something that's not going to interact. You notice nitrate. Nitrate's no big deal because nitrate is already there, so perfect. We want to write the half reaction equations and the redox reaction equation. Okay, so there's your redox reaction equation right there. Your half reaction equations are right there. And now we want to write it in cell notation. So let me see if I can shrink this up a little bit. There we go, and I'll move it down. Okay, now the half reaction cell notation, okay, real simple. We're going to take the anode, which is the left-hand side. So on the anode side, we have Fe solid, boundary change, because we're going to Fe2 plus aqueous, separated by the salt bridge, and then we're going to have the cathode reaction, which is going to be nickel 2 plus aqueous, boundary change, nickel solid. So remember that this is always going to be the anode on this side and the cathode on this side. Now some people say, well sir, is it always going to have to be as you got it written? You know, is the anode always going to be on this side? Well, not really. This is just so happens that I chose to put iron in this on the left-hand side. I could have put iron here, in which case the electrons would have went back the other way. Right? Because iron is going to be the source of electrons. So if I flip this over, then the electrons would have went the other direction because iron is going to be the anode. Okay? I chose to put the anode on this side because it fits nicely with what's happening up here and the fact that it's anode cathode. There we go. Okay. Sometimes we see redox occurring with different ions and gases. So in this case, what we need in the examples that we've just done here, the iron and the nickel were the electrodes. That was what the electrons were. You know, as this reaction produced electrons here, the electrons needed somewhere to go, so they just moved up this piece of metal and then onto the wire. So because this reaction is happening on this piece of metal, this is being referred to as an electrode, and it's a special type. It's called the anode. It's an electrode. In these examples over here, we don't have any metal. Europium 3 plus is being converted to europium 2 plus. Both of these are in the aqueous phase, so we need some way to get the electrons out of the solution and onto the wire. And in order to do that, we're going to use something called an inert electrode. An inert electrode. And the inert electrode is going to be something that's not going to be chemically reactive with what's going on in the in the beakers. And basically its only function is to serve as a surface for the transfer of electrons. Okay? Sometimes it's referred to as a catalytic, you know, it might catalyze the reaction as well, but in this case it's going to be inert. So we could use things like platinum, palladium, carbon rods. Depending on what's going on in the container, it might be a nickel rod, and we'll talk about, you know, being able to choose an electrode later on when we look at the voltages that are being created here. But for now, if you want to pick something that's safe, pick either platinum or copper. All right, and that way you can't go wrong. So if we do a little half cell of this particular reaction, we're looking at this and we're saying, okay, we can take a beaker here and another beaker over here. I'm going to make this beaker a little bigger. Doesn't matter. Okay, in this half cell, I'm going to have a piece of zinc, and in this half cell, I'm going to put a piece of platinum. So zinc and, no, platinum, yes. Okay, I'm going to connect it up with a wire. I'm going to have my device that's going to burn the electricity, you know, like an iPod or a camera or a light bulb. The zinc is going to be immersed in zinc ions. And the platinum this time is going to be immersed in europium 3 plus and europium 2 plus. Okay, so what's going on? Oh, I forgot my salt bridge. Never forget your salt bridge. You'll lose a mark on the test if you forget your salt bridge. We need some way of maintaining electrical neutrality. Okay, so what's going on in this particular cell? Well, we've got zinc going to zinc 2 plus 2 electrons. How do we know that? because up above in the shorthand notation, the zinc is the anode. The europium equation is going to be the cathode. In particular, the platinum is the cathode because that's the surface that the electrons are moving on. All right. So if electrons are moving up to, the electrons are moving away from the zinc in this case because this is negative, so the electrons are moving this way. They're moving to the platinum. And we know from our shorthand notation up above that the europium 3+ is picking up an electron to produce europium 2+. So what's happening is the europium is coming in contact with the platinum, and as it does so, it changes to europium 2+ by picking up that electron. So platinum is not involved in the chemical reaction. Platinum is simply acting as an inert electron. Now, you notice the shorthand notation here? Just move this down a bit. The shorthand notation has europium 2+ and 3+ separated by a comma. We're not using a barrier here, are we? Because these guys are in the same phase. They're both aqueous. However, because platinum is in the solid phase, we have that separated by a barrier line, indicating that now we're in a separate phase. Okay? So that's why there's a comma between the europium, because they're in the same phase. There we go. Okay. Here's another one. It says we want to write the half-cell notation and sketch the electrochemical cell. And in this case, we want to assume an inert electrode for the chlorine that's going on here. So here's another special way of doing this, I guess. And I'm just going to draw this cell here. Okay, so we'll put, again, I'm going to put nickel on this side. Okay, and what we have going on here is we've got nickel solid going to nickel ions. And we know that because that's what's happening right here. And in the other reaction, we're going to have chlorine gas being converted to chlorine ions. Okay, so my half-cell notation, or my shorthand notation, is going to be this, the anode followed by the cathode. Let's do the cell before we do the shorthand notation, because we want to be able to see what phase changes we have here. And here we go. Now I'm going to take a graphite rod, and I'm going to do that as a solid rod here. Graphite generally comes in as a rod. Okay, but the size of a pencil or so. So this is going to be my graphite rod. And what we're going to have is we're going to have this hooked up, of course, to our flashlight or whatever. Okay, we're going to have a salt bridge here as well. Got to have a salt bridge. KNO3 in it. All right, now, and the salt bridge has to be immersed too, by the way. If the salt bridge is not down in the solution, I've seen that on public exams. Some people will write their solution level down here and will say, well, that's not going to work. How can that cell work? The salt bridge has no way of getting its ions. The ions are not allowed to jump through space, right? They have to flow through the solution. So you have to make sure that your salt bridge is immersed in the solution itself too. Okay, now the carbon electrode, here's a different situation. We've got a gas that's going to be required to get in here. So what we do with this guy is we have a special little container that looks something like this. It's like an upside down test tube that looks something like this. And this test tube is going to be hooked up to a chlorine tank. All right? So as chlorine gets pumped in, chlorine gas is being pumped in here, you're going to start seeing bubbles. Blub, 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 right? And the chlorine is going to come in contact with the graphite rod, so my electrical current has to be connected down through there. And there we go. So what's going to happen here now, as the chlorine is pumped in as a gas, it's coming in contact with the surface, and as a result, what's coming out of here now is going to be chlorine ions. Okay, over here, I'm going to take my nickel, and it's going to produce nickel ions. So this is going to be my anode, because this is the site of oxidation. And this, of course, is the cathode. The carbon is the cathode here, because that's where the site of reduction is, right? The cathode is the site of reduction. And what we have for our shorthand notation then is this little, let's see if we can figure it out. We've got nickel solid going to nickel ions. We see a boundary change here, separated by the salt bridge. And then we have chlorine gas undergoing a boundary change because we're producing chlorine ions, which is happening on another boundary with a piece of carbon rod. So there we see two boundary changes because we're dealing with gas, an aqueous, and a solid. And there we go. Anode, cathode. Okay. Which way would the ions move in this case? Well, remember, anions to the anode. So in my salt bridge, anions to the anode. So that's going to be nitrate moving this way. Cations to the cathode, which makes sense in this case because if we're building up chloride, more and more chloride is being produced, then we're going to pull the potassium in this direction to try and neutralize it. So again, the salt bridge, its purpose is to neutralize each half cell. There we go. Okay. And last but not least, we want to look at what a battery is. Now, one of these cells by itself is not going to produce a whole bunch of electricity. The voltage is going to be pretty small, actually. So if we had, say, a 12-volt car battery, it's going to be difficult to create one single cell to produce enough voltage to create 12 volts. Likewise, like a 9-volt battery. What we need to do here is we want to be able to create, we can put several batteries in what's called series. So one after the other. And in this particular reaction that we just done, the very first one, we had zinc. So you can make your own particular electrochemical cell here by getting a lemon or a lime or a kiwi or a potato or an apple or anything like that. What's happening is the acidic environment in the piece of fruit is acting as the electrolyte and porous barrier. All right, the fruit itself is going to restrict the movement of ions so that it can control the electrical neutrality here. The zinc, we could take a zinc nail, like a galvanized nail, hook it up to a very small device like a little tiny digital clock or something like that that requires a very small voltage. And we can get a piece of copper wire and stick down in the other side of the lemon. And when we hook it up, you're going to see a small glimmer coming through the light bulb. Now, if we want this light bulb to be brighter, what we're going to do is we're going to make this in series. So we're going to get 4 lemons and 4 pieces of galvanized nails, so 4 4-inch nails that are galvanized, 4 pieces of copper wire, and we're going to set up our battery in series. So whatever the voltage is for one of these, we're going to get 4 times that voltage, so the light bulb is going to run brighter. So for our cells, what we would do, if each of these cells produces about 1.2 volts of energy, by hooking them up in series, we can get a total of 4.8 volts coming out of this, which is going to be more powerful, and it's going to be able to make our light bulb brighter. And there we go. So a battery is a group of electrochemical cells arranged in series. All right, so that's how a 12-volt car battery is. There's several cells within the 12-volt battery itself. Okay, I'm going to stop there. If you want to read up on this, which I recommend you do, okay, make sure you consult page 756. Have a read about cells and batteries as well, and find out what the names of these batteries are, because they come up as multiple choice as well. And here's a few practice problems. Go get a couple old public exams, have a look, see if you can do them. And if you have any trouble, fire some questions off to your online tutors, or fire them off into the discussion posting, and I can see what I can do for you. All right. See you later. Bye-bye.